Today I'm going to talk about this particular niche area of edge intelligence. There is a lot of special issue, lots of activity in conferences and journals in this area. So I hope to give you my perspective on the data science of the Internet of Things and how this area is changing, how data science is adapting to the big data coming from Internet of Things. So we have all these things connected to the internet, and it's not just sensors, although today I will focus on sensing. It's not just sensors. So here you see Raspberry Pis going all the way down to skin sensors, and there is a variety of objects and devices that are connected. They generate lots of data. Arguably now is the majority of data in the Internet of Things goes into the cloud for analysis. So some questions I want to discuss today, to visit today together with you is, first of all, how data science can and should be applied to the Internet of Things and how it should change. And by data science is much broader than machine learning. So as part of this discussion, I'm looking at the quality of data, but I will be also looking at the machine learning aspects, so embedded learning, as in the attempt of doing some machine learning in devices, in small devices. So the one thing that is very important about the Internet of Things is the reliability or unreliability of sensor data. Data coming from the Internet of Things for sensors is unreliable for a variety of reasons: hardware, software, so on the devices, but also communications. And some of the antennas, for example, if you look at this, is Telos B device. It has an embedded antenna that is extremely cheap and unreliable. So a lot of the missing data or chunks of data that are missing, that are transmitted or are not transmitting to the cloud, is because of communication problems, of spectrum limitations, but also trying to maximize the battery duration, so the energy efficiency aspects of the sensors. So there is a number of reasons why the data that you are using in the cloud coming from sensors is highly unreliable, cannot be trusted. And as any data scientist will say, if you have unreliable data, your models will not be trusted. So it's garbage in, then it's garbage out. So how far can we address this problem of unreliability? I will show you through a number of pilot studies that this is really a major problem. It's not just a small issue. And then once we go this far, how can we miniaturize machine learning? How can we get machine learning to run into smaller and smaller devices where there's limitations in terms of memory, CPU, but also energy constraints? So how far can we miniaturize machine learning? And once we've done that, what else can we do with that? So I will refer to that as edge learning, as referring to the fact that you are running some machine learning, shallow learning, up to, I will show also some sparsified artificial neural networks. What can we do if we are running machine learning in the background at the back of those devices? So let's start with a little introduction about data science. The data science of smart sensing is quite unique. Is unlike any other area of data science where you have medical data or you have data already pre-curated. In this example, what you see here is that you are subsampling a broad area. So you are collecting data continuously from sensors, but these are actually sampling the territory. So you don't have a full coverage of a broad area. So this is a city and you are measuring things. In this case, it's traffic. I will look at this pilot later. And the information you have is punctual, is not uniform, is not covering the whole area. So typical problems that we are looking at is, first of all, you never have enough data. So statistical significance that you want to achieve, always want to achieve before you can do any prediction models on your data, is a big critical problem because here you're dealing with a spatio-temporal series. So you have different, you're looking at the timeline, and the granularity of the timeline is important, but also the granularity of the space. So how many sensors you have in the area that you're monitoring, and the granularity in the space and in time is quite limited. So it's very hard to have enough data for all the area that you're monitoring typically. The second important problem I want to point out is data fusion. So you have heterogeneous data, so coming from different sensors. This is what I refer to as objective data. It's heterogeneous. It's it's not just one type of things that you measure. And you want to correlate heterogeneous sensor value, but you also have, because sensor systems now interact with humans. So for example, in a smart city scenario, you have data coming from the city, but you have data coming from people. So you have an interaction between smart people and smart cities. And then you have a mix of objective and subjective data, and you want to do data fusion of this this variety of data. It's extremely difficult. So you don't have enough, you never have enough, especially when it comes to subjective data. It's very hard to collect information from people. So it's very hard to get that. And I will have an example precisely on this towards the end of this presentation. The third important problem is that the data, as I was mentioning before, is intrinsically not to be trusted. Because it comes from cheap devices, it comes through from communication systems that suffer from interference and spectrum limitations. So you have unreliable data, and when you have your data, it's typically incomplete. So there is collection constraints in the Internet of Things, in the data science aspect of the Internet of Things. You have constraints from the probes and from the communication system. So the data that you have is always limited, and as we will see is never enough. So my argument today is that these intelligent processes must start at what I call the micro edge. So the micro edge is the probes and the sensors where you're collecting information. So you need to do, and I will try to show the value of concurrentently sensing and learning. So you're running machine learning in the background. So while you're collecting your data, you can profile, you can clean, and you can pre-compress, and you can do a lot of interesting things in the sensor. Now, a small parenthesis on data science for those of you who might not be familiar with data science, but this is just really a couple of slides to allow me to introduce the data science of IoT. So typically what you have data from one side and you want to make insights from the other side. There's a lot of things happening in between the process from data ingestion all the way into building and achieving your prediction models and your visualizations, so making the insights. There's a lot of things happening in the middle there. Typically, the data science cycle, if I want to really summarize that in one slide, it's something that looks like that. You get your data ingested, it's raw data. You need to go through a data exploration and curation process. This is the bit that is very hard to do, as I will illustrate in a minute, very hard to do in the Internet of Things because it has to be done in real time. And then once you can trust your data, essentially you're curating and you can trust your data, then you push that through a number of machine learning techniques until you get the right one. Essentially, it's a trial and error process, both here on this side, on the data curation side, and on the machine learning side. Another argument I want to make is that this curation of your data here in the case of the Internet of Things is very valuable to use machine learning for that. So you're using machine learning to clean the data before you use machine learning to build the prediction models to make the insights on the data. They're using machine learning at all levels. This is pretty much an art because any of those things that you see here, they are done through a lot of trial and error. Data scientists that typically divide into two groups, those who are curating the data and those who are building the models. And sometimes it's one team, sometimes it's two teams. But in any case, the work is done through trial and error. So there is no predefined techniques that takes you from raw data into visualization. There's a lot of art happening in the meantime. And by the way, this part, it is well known and well documented that it takes most of the time. So the data curation is considered to be the least interesting one. And that part is where you're building, you're working your deep learning, you're making your insights is the one where there is most focus. However, this bit is the one that needs more attention in the Internet of Things. And once you've sorted and cleaned your data, that part in the IoT is relatively simpler. Okay, how is this implemented? Typically, you have your data, you push your data through connections and internet. Anyway, you end up having your data somewhere into the cloud, and then you start the whole data science process from cleaning into prediction modeling. So how is this changing in the case of IoT and mainly focusing on smart sensing. How is this changing? Well, it's quite different because if you look at the same diagram before here, you have your data probes, your sensing elements, your sensor nodes, and a lot of hardware there scattered, and most of the times this is battery operated or with significant constraints in terms of the collection process. So you have your probes distributed throughout the monitor system. Then you take all the stuff, all the raw data, and you push it through connections and you get that into the cloud, and you kind of do the same like for any other system. Well, so you go from the data collection, which is a distributed process, while in other data science systems, data collection is not distributed. You have all your data in one database, and then you can digest it, but then you need to collect your data, you concentrate it, you push it through the cloud, and then you make your insight. Well, my argument is that going through a typical data science process in this way is not effective. So what you have here, you have lots of, first of all, is a massive scale of distributed data, but this data is often uncorrelated, very hard to correlate, is unstructured, and it's very hard to do the data fusion because of these differences and heterogeneity in the data. A lot of data is not interesting, is irrelevant, is absolutely not. For example, if you're transmitting temperature values and the temperature is not changing, all these data series of temperatures for a long time, they're really not important. They're not interesting. You are more interested in special events or anomalies that occur in the data than the normality. The other aspects is the missing data problem. Missing data problem is well documented, well known in data science. In this case, it's very, very hard to tackle. I would spend quite a bit of time on the missing data problem in the IoT. And then I mentioned that is unreliable data. So what we are doing when we do cloud-based IoT systems, which is the major approach in industry at the moment for obvious reasons, we are going through a brute force process. So we take all this raw data and you transfer what is, I would say, an unpredictable mess. It's very hard to do anything because it's very hard to clean the data as an after process. As my argument is, you need to do that at collection time. Okay, so that's exactly what I would be talking about now in the remaining of my time. How to use shallow learning, so it's not really the deep learning sort of machine learning side. How to use data learning to perform a lot of things, mainly in the data exploration and curation side at the edge, so in the nodes that are collecting the information. And then what you are pushing here towards the cloud is pre-curated, pre-filtered, pre-compressed set of data streams that have been partially aggregated, possibly partially aggregated with anomalies, and possibly you are transmitting only those bits and chunks of data series that are interesting. So you can pre-find some anomalies and determine events of interest and transmit to the cloud only the most interesting bits. And that will also facilitate also the deep learning part because you're doing learning on curated data. Okay, let me just stop with the introductory part and get into a number of projects. So I'll use all my time talking about projects, pilots that we've been working on for a number of years, and then time permitting, I'll cover all of them or just some of them. So first one is the idea was to do some machine learning on unreliable sensor data. So the problem is, how can you build prediction models where your sensor data has missing data and errors and faults in the data? And you will see from this example that we have systematic errors that last for quite a bit of time. So they're very hard to distinguish the errors from the normal data, because the errors last for quite a bit of time. So typical outlier detection problems techniques are very hard to use. So it's not individual points that are faulty, but bits of the time series. You have sustained anomalies. And the other aspect here is that you have a big data problem, obviously, because there's lots of data coming, but you also have a big missing data problem. So there's a lot of data is missing. And the interesting thing here in these particular scenarios is that What you are really interested in is the missing data. So the data that you ought to have that you don't have, because there is a lot of interesting things happening while the data is not being transferred to the cloud. And these are typically special events, and you will want to capture that, and you completely miss those. Okay, this is a mobility tracing pilot in Cairo. See, there's people also connected from Sardinia. There is open data collected by some sensors scattered around mainly the center part of the city. And you are talking about sensors embedded in the road, so they can measure things such as flow, speed, or of vehicles coming around. So this data dating back from 2016 with daily entries in the range of 140,000. So there's quite a lot of data coming here, but this is not quality data. So the question we had when we started this, obviously, this is during the lockdown, we wanted to say there's data there. Let's try and look at the mobility patterns and how those mobility patterns are changing during the different pandemic stages. Except that we couldn't solve this problem. We got stuck because there was no point in pushing data, this kind of raw data into the cloud. We couldn't make sense of it. And here is why. This is just a fingerprint of the data. There are different sensors, and here you see the timeline. And what you see here in white is the missing data. So you can see there's big holes in the data. The missing data in this case is not the majority, but is a good chunk of the data that we have. So what's happening during those times where there is no data is for transmission problems or for hardware problems is not reaching the cloud. So you have missing data, but then you also have some data that comes to the cloud, but is completely wrong. And these two areas are of real concern. These are the two reasons why we couldn't process the data right away. So what you see here, if we look at the data, so that the dots here is the actual data coming from one sensor, and the regression line that if we try to build a regression line with any machine learning algorithm or working on time series, the regression line of this traffic, it picks here. It's quite an amazing pick. It goes way above what the physics tells us about how fast cars can go in a city. So if I zoom in into these periods, essentially this period is the Easter period from last year, and there was total lockdown in that area. Well, in Italy, there was total lockdown, and during the lockdown, this data is telling me that there is an amount of traffic that is way above. It's off the scale. So during Easter time, there was lockdown and there was exceptional amount of traffic. So if you just push the data through machine learning, it doesn't make any sense because there's systematic errors there. And these are not rare events. It's quite typical from real sensor systems that you get this kind of very strange off-scale results. So here in this wide window of time, you have missing data and you have wrong data mixed up with proper data. So the problem then is that there's no point in trying to check what happens during lockdown in that particular city because the data is obviously wrong. So what you can do with that, if you look at, if you just look at the trends and seasonality of the data, you see that during that Easter period, Easter break, there was a massive change in the trend of the data. This is typically associated with a real event, which is not the case in this case. If you look at the seasonality, the weekly seasonality, this is also wrong, completely wrong, because obviously you don't typically have traffic going down during the week and up during the weekends, and you don't usually have this trend. The daily trend is also wrong. You have more traffic during the night and no traffic and less traffic during the day. So it's obviously everything is wrong, and everything is wrong precisely because of faulty data transmitted by the sensor. So it's not because of missing data, but because it's wrong data. So would you feed this data to a proper machine learning algorithm? No. So the focus of the project shifted from data modeling into data cleaning. And it took us quite a long time to clean that. So it's Easter Sunday again, and if we just push this data through Prof, and then this really requires quite a bit of heavy computations in the cloud, so it's not something you would do with edge learning, which is the main topic of today. Then what you do is in the red, you see the anomalies, and you can see that most anomalies have been detected. And the missing data in this area, they're also captured. And if you go one step further, you can actually build the, you could make a data imputation problem, you can solve the data imputation problem. And the blue line that you see here is the imputed data. So it's you eliminate the anomalies and then you fill in the gaps coming from having removed the anomalies and from the missing data in the first place. And what you see here is something that now makes sense because you see that during this Easter lockdown period, you do have a decrease in traffic, significant decrease in traffic, which is what it should be. And then the whole line fits a bit more nicely. And you see the periodicity here for the weekends and weekdays and so forth. So all this to say, you need to do quite a lot of data cleaning before you can do anything interesting with the data. So now if we look at the original data and we look at the trends and seasonality of the data, that was completely wrong before, and it makes sense now. Okay, I want to now skip from cloud-based learning into edge learning, which is the topic I'm talking about here. In this case, the idea was, can we take a clean data set, so that now the data is a bit cleaner, then we take a clean data set, we impair it in various ways. So we simulate real-time situation where the data is impaired. And when we try to use edge learning, so machine learning in the nodes, in the sensing nodes, edge learning to reconstruct the original data. I think I was just saying that what we're doing is starting from a clean data set, impair it in various ways, and then try to recover the original data set with, with some edge learning techniques. Now, in this case, we're starting from pollution data set, just to change from mobility into pollution. And what we have a number of features that are in the data set, but mainly let's focus on the ozone level measure. This is a typical distribution of the values that you have. Can you still hear me?
Yes, please go ahead.
Okay, sorry for connection problem. We are talking about Internet of Things that you can't even connect at home. Okay, and what we have is a range of samples at the time series at interval of 5 minutes, quite a lot of samples. And what we do now, then we started impairing all this data and then trying to restructure the impaired data. Okay, so what we see here is different levels of contamination, or rather impairment levels. So we are plugging holes into the data set, starting from 0% up to 100%. So you're removing all the data. And then a variety of machine learning algorithms running on Raspberry Pi, they will rebuild, they will do the data imputation for us. And we can check here, because this is the error that we have. We want errors to be minimal. So we can see here as the machine learning algorithm, particularly this KNN and Miss Forest, are able to do data imputation with quite high accuracy, because you can go from up to 50% of missing data and reconstruct that with an error with an RMSE of 10. So it's quite acceptable threshold for data science in general. Okay, so what we see here also, if we are using simpler methods, for example, mean imputation. Mean imputation is where, when you have a missing data, you replace it with the mean value of your neighbors. In this case, is not working, is not able to replace your data. So that shows you the value of using some simple machine learning or data mining methods that can run on Raspberry Pi if they are properly tuned, and that they can reconstruct your data quite well. So you can look also at the statistics of that. Essentially, the brown line and the blue line, they are completely overlapping. So the reconstruction of your data is very, very accurate. And this is the statistics where you're plugging also 50% of, you're eliminating 50% of data from your data set, and you can rebuild your data set with such accuracy. Of course, you can look at the box plots and other things, okay, but the essential message here is we can reconstruct up to quite high values. So here we're going for 60% of random impairments, and you can reconstruct your original data set very, very accurately. Get my laser pointer. Now we tried a different experiment. So if you have bursty impairments, so you're not losing one data at a time, but you're using chunks of data, which is typical when you lose where we have poor connectivity. You don't typically lose one packet, but you lose a train of packets. Then the problem is much more challenging. And the question was, can we still reconstruct the original data, and how far can we go? Well, what you see here is we have burst size up to about 20 data points, with overall 20% data has been impaired from the data set, and we can reconstruct quite well the original data. So we start from the original clean data, we impair it synthetically, so artificially, and then we use KNN, MIS4, MICE, and a number of other algorithms, machine learning algorithms, to rebuild the original data set, and it works quite surprisingly. So the value of that is that you can actually you can do a lot of things with your data to increase your data quality when it comes to using some standard data science methods at the edge. Okay, this is just to give you an impression of the computational time you're using KNN. Apologies for those of you who are not familiar with these algorithms, but this is a simple data mining algorithm, clustering, and essentially what the algorithm is doing is replacing the missing data with the mean value of the closest neighbors. So no, that's just to say it in Impairments. And we're talking about a few seconds to rebuild a data set across the whole data set. And if you run that on Raspberry Pi, just a few tenths of seconds, takes a little bit longer, but this is running on the whole data set. Obviously, you can then further optimize the problem, work on smaller time windows rather than working on the whole time window. You can split it up, and then you can run these things in real time. All right, this is what as far as I wanted to go with this example. I have another example I'm quite keen of introducing for micro edge. So here we don't have a Raspberry Pi, which is quite powerful, but we have inexpensive sensors with 10, 20 kilobytes of RAM. So really very difficult to miniaturize those machine learning algorithms and to get anything valuable out of them. Well, we have two examples here. One is discussing some anomaly detection with very simple shallow learning on this sensor, this Telos B, and the other example is using reinforcement learning. So let's look at the first one. This, again, we are concurrently sensing and learning. So the system is able to detect very simple patterns. These are some of the algorithms we tried out. There are some more, of course. These are very simple shallow learning algorithms, obviously, because you're talking about 10 kilobytes of RAM. So there's not much that you can do. And also data rates are pretty limited. So what you see in this, we'll see in a minute in this animation, is that the system is working on small observation windows, but is learning simple patterns. And as you see, if I start this here, you will see this LED is flashing red when it's self-calibrating, and I'm tapping on a light sensor. So the system is learning this tapping pattern, and at some point it's flashing green here. I don't know if you can see this on your screen. Essentially showing is learning the patterns and also being able to remember this pattern for a while. So that again, we're not talking about advanced machine learning here, but through these simple processes, you can differentiate from normal data and abnormal data without having to pre-program your sensor. So you can automatically detect thresholds of normality in your data and detect anomalies. This is a very useful way to pre-filter the data that you will send up to the cloud. So typically you can send only the anomalous data, and the normal one, where nothing is changing, is not interesting. So you don't need to use the network for transmitting that information. Okay, I have a second example here, where we've been running Q-learning. Q-learning is a reinforcement learning algorithm. So it goes already one level up. It's not shallow learning. It's doing quite interesting things. In this case, what we're trying to do, and you see here the values that you are trying to determine, so the threshold, the optimal threshold that you're trying to find, the y-axis, and this is the timeline. And this is a trial and error machine learning algorithms. So the algorithm is attempting different values for transmission power, or you can use this for selecting the best frequency, for example, for transmission or for other objectives. So you're using this trial and error, and the system is getting some feedback, and from the feedback that the system is getting, you determine gradually over the time, you determine the optimal condition, transmission condition for this sensor. So this is used in this particular example for saving energy. So it led to saving, if you're working in deep sleep mode, we could save up to 23 days of battery life. So it's quite useful. And again, this is not being done in the cloud, it's being done through embedded learning. So in this case, reinforcement learning. Okay, the time I have a couple of more examples, and Giancarlo, feel free to stop me at some point, because I can cover more of this also later. So another element is, okay, we talk about shallow learning in sensors, we talk about some simple reinforcement learning in sensors. Now, what if we want to do artificial neural networks and we need to squeeze it? Of course, you need to do something else. It's very hard to do artificial neural networks in Raspberry Pi on small devices. Well, this work was started in 2016, where PhD students of mine came up with this idea of using network science to sparsify the neural networks before training. So that this, well, you can see the reference here to this seminal paper that was describing this idea to mimic biological neural networks. And so instead of attempting the training of a fully connected networks, the idea that he had was, why don't we try and make the network more like natural networks before we train it? And there we managed to reduce the number of links that you need to train by 2 orders of magnitude. So it's quite a lot of saving, and you are actually miniaturizing your artificial neural networks by using these techniques that we call sparsification. Then we went on and we said, oh, well, what's the point in simplifying, sparsifying the network before the training? Why don't we try and sparsify it during the training? So at each iteration, you keep your network simple and you sparsify that. Anyway, there's not much time here to get into the details, but I want to show you some results, because this gives you an impression of the possibility of miniaturizing artificial neural networks and running them on fairly small architectures. So here's some results. Somebody else took the code, the original code, they optimized this code, and they managed to, they ran some benchmarking on different data sets, quite big typical data sets here. And here's the number of connections that you need to train before you have satisfactory results. Where with sparsification, you go from this range, we are talking 10 to the power of 9 number of links. With sparsification, with simple tricks, you have neural networks that they go way beyond the million of connections. Well, by the way, this is a 1 million multi-layer perceptron running in a laptop without GPU, and that's the reason why you see this picture here, is because this is pretty much the size of the brain of a frog. So you can kind of mimic the neural network complexity of a frog in a laptop, in a simple laptop, and then you can also go down to Raspberry Pis. Okay, now wanted to mention my last example. In these cases, I'm talking about hybrid learning. In this case, we have objective data coming from sensors and subjective data coming from people. This was a trial study, quite a broad trial study done in collaboration at Derby University with psychologists, where the problem was collecting subjective data in across the city, which is a very broad area, and achieving statistical significance is, I would say, almost impossible. Because if you look at how many answers you can get from subjects, so many times you can pop up into their cell phone a question and get them to answer, and you want statistical significance for every location in the city, well, you would need to collect just too many samples. So in this case, what you can do, you can use the objective data, such as location, mobility patterns, and other information to guide the subjective data collection process. And that's what we've done, because this is a quite complex spatio-temporal data set. It's something where you want to know where, in which area of the city people feel more satisfied and try to find out why. Obviously, these are the green areas in the city where people are more satisfied. So you will want to use all the objective data that you have to fire the questions only when you're far from statistical significance or that particular questionnaire in a particular area in the city. Okay, so in this case, this was quite a big trial. If you consider a typical subjective studies, we have almost 2,000 subjects involved, so people involved throughout the city, observing their answers and their movements and their behavior during a span of 30 days. And we, of course, have objective data coming from the app because this data collection was done through an app. And again, lots and lots of inconsistent data. So what you have, the data you're collecting is inconsistent because of errors, but it's also inconsistent because it comes from people, and people are not always able to answer objectively. That's why we say they are subjective studies. They're not able to give you an exact answer. So if you ask people if you are in that particular moment, if they are happy on a scale, and they may give inconsistent answers if the question is fired on different days and on different locations. Okay, so it's very interesting to develop these techniques. Anyway, what we've done, we developed a simple chatbot running in the mobile phone. So the chatbot was collaborating with the cloud, and it was possible then to fire the questions at the right moment in the right location. And the right moment and location is those locations and moments where you would be missing subjective responses. So in this case, if you run this subjective study at random without a chatbot, you see the blue line. So this is the time it takes for a subjective study to be completed and reach statistical significance in days. This is over 125 days. We were running our system for much shorter days. And if we are using chatbots running and fusing objective data with subjective data, that's how far you can speed up your subjective study, because you're not firing useless questions in the wrong place. Okay, this was my last example. There's much more to say, and there are papers describing this, and of course there's much more to say, but unfortunately I think my time is almost up. So I would like to use a couple of more minutes to wrap up some concepts that I would like, some message I would like as a take-home messages for you. So the first bigger one is that starting your data science in the cloud is just too late. So doing cloud-based IoT for me is missing a lot of opportunities. And I hope I gave you through some practical pilot studies reasons why this is the case. Because you will end up working on unreliable data. If you can't trust your data, it's very hard to make sense of it. So you are missing opportunities here. So smart sensing, if you want to do smart sensing, my personal experience so far working on this area is that you should go beyond cloud-based processes. I'm not saying to replace cloud-based computing, it's just complement cloud-based computing. So the key messages I try to convey today was, first of all, that embedded learning, so learning at the edge, allows us to do data science in a new way. For example, we can do live data curation, but mainly working on data reliability at the edge where the data is collected. So it's right there, so you can curate it and then before transmitting it to the cloud. But once you are running machine learning at the edge, there's so much more you can do. So you have machine learning running in the background, say KNN running in the background all the time. It's not just for data imputation. You can use it for detecting the faults in the hardware faults, communication faults, any sort of anomalies in the data, in the hardware, in the software. You can also do some pattern matching. And the one thing I'm quite keen of doing, and we're working quite hard with my team on this, is working on missing data. So if your probe is missing some data, the best location to correct that error is at the probe level. It's not to do that, to try and do that later on in the cloud. Okay, you can also do a lot of self-optimization. So for example, with energy and spectrum problems that you always have during the process of collecting your data, you can self-optimize the process because you can find out when your data stream is more interesting, and you can select the interesting data for transmission. That allows you to save battery, to save communication, but also to get into the cloud the most interesting data, most relevant data. Of course, you have to be careful as which data you drop. The one thing message I would like, if I can leave with one message, is that learning, the best thing to do is learning while sensing. So not to decouple those things, which is typical thing. First, you think about collecting your data, and then you think what to do with it. You need to learn while you're sensing, because machine learning, if you can miniaturize it and do embedded learning, machine learning is not an afterthought. It's something that needs to start at the edge and then continue throughout the whole data science process. The other thing that I'm not sure how many of you have been focusing on this aspect is this missing data problem is not a small data issue. And through some examples I was showing you at the beginning, on the first case study, the missing data, it's a good chunk of the data that you are dealing with. So it's not small data issue. It's a big missing data issue that we are dealing with, because there's a lot of faults that can take place in the probes and throughout the whole collection process of an IoT chain. So you have lots of missing data. And these are typically the most interesting data that you will want to have. The other aspect I only briefly mentioned, the last case study, when you're doing smart sensing with humans in the loop, and you can imagine a number of situations where this is the case. I give you an example where you are trying to carry out a subjective study through digital technologies, where you are doing smart sensing in many directions. Well, in this case, this is very, very challenging. There is a lot of work I've done in the past, which has not been described here, as to why it's so difficult to process subjective data using typical machine learning algorithms, because machine learning algorithms work well when the data is reliable, when the data is statistically distributed in the right way, while we have lots of inconsistent answers coming from humans, and there are techniques to look at specifically this problem. For those of you who are interested, please send me a note after the presentation. I can send you some pointers as to how we can improve subjective studies using machine learning. Then there are many other interesting issues I couldn't talk about, also because this is not my area of expertise. For example, a lot of ethical, privacy and security problems should be addressed starting from the data source. There are many reasons why there is no point in doing data anonymization in the cloud, where you might have infringed a lot of laws in the process. But anyway, this is not an area that I'm investigating, but perhaps good ideas, food for thought for some of you who are into privacy, security, and ethical issues of data, to use some embedded learning to start the process at the edge. And this is I think all the time I had for. Thank you very much for listening. There's much more information that you can find, but if you have time for just two papers, to read two papers, I would recommend those two papers. This one, the top one, is the one where we talk about smart anomaly detection in sensor system. We provide a review of smart anomaly detection or machine learning at the edge. So it covers state of the art up to end of 2020. And at the bottom here, you see another paper. This is a seminal paper that we published in this idea of sparsification of artificial neural networks so that they can run on embedded architectures. Anyway, I think it's best to use the remaining time if there's any questions. And if we can't cover all the questions, please put them in the chat and I'll try to answer them later. Thank you very much for listening.